I am at the Greenwich Observatory in London, hence this fantastic rainy British spring weather, and I'm here because I wanted to see line 0. This is it, the prime meridian. This is what defines 0 when it comes to longitude. So your GPS will show you exactly 0 if you're on this line, except it doesn't. 0's not here anymore, it's over there in the park. It's true, I'm right on, well, I'm not right on the line. I'm currently in the Western Hemisphere, Eastern Hemisphere, on the line. And if I get my GPS right now, it is negative 0.00143333. And obviously our phone is not super accurate, but it is accurate enough to show me this is not 0. And if I walk around trying to find 0, it's about 100 meters that way.
Obviously this annoys tourists who visit the line, look at their phone and realize it's not actually on 0. And to give you a sense of what that might look like, we have a dramatic reenactment by my mate Steve Mould.
If I could leave the Greenwich Meridian 0 stars, I would.
It was actually Steve who originally told me about the 0 line moving, and he kindly joined me to make a video about it.
Now, because this is a stand-up maths video, we're going to do things very thoroughly. So we're here on the incorrect 0. But for completeness, I know later on I've sent Future Matt to go out into the park. In fact, Future Matt, we have Future Matt with us right now. Are you there? Yes, we're here in the future on the line in the park. How are things in the courtyard? You know, it's all going pretty well here. In the courtyard, apart from the disappointment at the 0 line is in the wrong spot. Everything's great in the park. Yeah, I mean, is your Steve complaining about the premise as well? Yes, yeah. Yours? Oh, absolutely. All right, so we're going to hand over to both of you in the park. Thank you very much. So we spent a while walking around earlier. We had out your phone, looking at the GPS location on Future Steve's phone. And we found it. This is it. Where it comes straight down there across the path and off that way. This is your proper 0 line. Should we label the line?
Yeah, right, great.
Okay, yeah, of course. So if we need to run a line north-south,
Okay.
this is the actual 0 line for all GPS. We're going to send back to Matt and Steve in the past. Thank you very much, Future Matt and Future Steve. Now, current Steve, just go with it, mate. Okay, so when you first mentioned this to me, and I asked, I was like, why? How can this not be 0 anymore? Was it ever 0? What was going on? I'm going to paraphrase what I remember. You said they were using the wrong down.
Yeah. Well, so the wrong down, the wrong up. Basically, when they were figuring out where the line should be, they needed a way of looking directly upwards.
Okay.
And it turns out that there is more than one way to define directly upwards.
Because we're looking at the stars, which is why we're at an observatory.
Yes.
For a line.
That's the way to do it.
And we now use a different up.
Yes.
I know. So you explained this to me, and I don't know if I brought this up talking to you or on the channel.
Yeah.
Wrote a book about trigonometry.
Yes, and the US edition is out this August 20th. Details about the pre-order sweepstakes and free digital bookmark at the end of the video.
But in it, I wanted to mention this.
Yeah.
And so I thought, you know what, obviously your explanation, crisp, but I thought I'm going to dig into it a bit more. Okay. And what I found out
What did I get wrong?
No, you were 100% correct. You were totally on the money. But what I realized almost immediately is that this is not the line.
Oh, what is the line then?
This is the line. This is the telescope, actually. But the telescope is what defines the line. It's not like people worked out where the line should be in theory, and they had to calculate where to put this brass strip. The brass strip is just pointing, this is where the telescope is.
Well, it lines up exactly with the eyepiece of the telescope, in fact.
The eyepiece is the line. Nothing is the line. The only line is the eyepiece on this telescope. Everything else is just pointing to where that is. That's 0, which is quite pleasing because the eyepiece is shaped like a 0. So that is 0. And the reason it's on a telescope and it's not actually a line is because it's not really about measuring anything. It's all about timings. And for that, we're going to a different location. Before we get to the timing problem, we need to define some of our terms, which is why I brought this model of the Earth. And we got some tape.
Okay.
So, this is the Earth. The issue with the Earth is it's a sphere,
Yeah.
which makes working out where you are difficult.
In terms of like having an origin, like where do you decide where 0, 0 is? Like on a sheet of paper, you could say it's this bottom corner is 0, 0, but on a sphere, there's no obvious place to choose.
Famously, no corners.
Yeah.
We get one line for free. Or we get one line and 2 dots, right? Because the Earth is spinning.
Yes.
So we get our axis of rotation.
Yeah.
So north is the top of the axis it's spinning around, south is the bottom.
Yeah.
And we get the equator. So,
So we say, okay, 0 in this direction, in the up and down direction,
Yep.
we'll just define as the equator.
yeah, the middle bit, the middle bit.
So we already have a 0. It's the other one that is a problem. Okay. Okay, great.
We're going to mark that one.
So that's our 0 latitude.
Yes.
So you can have positive latitudes, like we're at positive latitude,
When you're up.
negative.
Yep, or negative, yeah. What we would love to have
Yeah.
is an equally unambiguous
0
0.
for this direction.
Yes, yes. And we don't.
If I said, where is the Paris Observatory? In the past, you would say the Paris Observatory is X degrees east of the London Observatory. But wouldn't it be nice if you could have a 0 so that everyone just
Agrees on
reference the
one,
same
yeah.
thing, and you can say London is here, Paris is here, instead of always talking in terms of relative to this, relative to that.
It was a big vote in 1884
Right.
where all the countries got together. Not all the countries, a lot of the countries got together. Had a big argument, took a vote, and where we're sat right now won.
Okay. Yeah.
Because Paris, I mean, the French had been using their own line, we'd been using our line, everyone else had different lines.
Yeah.
And then they decided it'd be easy if we all used the same one. There you go, do you want to mark us on there somewhere?
This is me taking a guess at what our latitude
No, right, okay, yes,
is.
yes.
Essentially, I'll put a
Good
cross.
enough. Great, great, great dot.
Thank you. But I did it as a cross. It's a cross between a dot and a cross. It's really
Oh, excellent smudge. So, you're here.
Yeah.
How do you work out your latitude and longitude?
Yeah. So
So,
you look at the stars.
you look at the stars, and right, okay, yeah. Okay, so turns out your latitude, how far up you are, is easy. Because if this is the Earth, and we're in this fantastic room at the Royal Observatory Greenwich, there are books and things everywhere around this room, around us.
Yeah.
We can consider them to be the stars.
Imagine they're the stars.
They're the stars.
Okay.
They're the galaxy around us.
Okay. Oh, relative to this.
Relative to this
great.
Earth.
All right, fine.
And yes, the Earth is going around the sun and all that jazz, but that's happening on such a small scale, it doesn't make a difference.
Oh, I see. So the fact that the Earth is kind of moving that way and that way and this way and this way because of its orbit around the sun doesn't matter because everything's so far away that they essentially don't move.
They don't move.
We'll assume they're infinitely far away.
Infinitely far away, but still visible.
Yes.
And so if there's like a star over there where the camera is,
Yeah.
and you're on the equator,
Yeah.
and you want to look at that star, it's directly above you.
Yeah.
Because you've got to look straight up because it's over there. But if you were up here on this dot and you look straight up, you're like, I can't see that star. I'm looking at a star over there.
Yeah.
And then what you can do is measure the difference between looking straight up over there. And you're like, I got to turn my telescope all the way down some number of degrees to be able to look at the same star that was overhead here.
Yeah. Yeah.
And the number of degrees you got to tilt it down? Latitude.
That's great.
That's so good.
So you could use so any star that is on that equatorial line, you could use that as
Now, I'm sure in practice, this is much more complicated than I've made it out to be. Like, I'm sure there's a bunch of stars,
Yeah, okay.
and we know the angles they should be, and you measure the angle you're looking at them with, I don't know, with like a telescope and a sextant or something, I don't know, right? but you can work out that nice and easy.
Yeah.
The question now is, why doesn't that work for working out how far? Because you think, well, it should work for this line, right?
Yeah.
Because if you're on this line, there's a star over there. We're producing a Colsat,
Yeah.
right? Directly above,
Yeah.
and over here you're measuring the same angle.
So you just tilt until you're looking at that star. So the issue is you have to know what time it is.
But that, yeah, exactly. The issue is this is happening all the time.
Yeah.
And the equator's fine. That's not going anywhere.
Yeah.
Because that's defined by being the middle of the axis of rotation.
Yeah.
So that's staying fixed, but this line's all over the shop.
Yeah.
So that doesn't help you. What you need to do is measure, if you're here and you've got the producing a coal star,
Yeah.
You need to measure as you sweep above it, what time is
Yes.
it overhead?
Yeah.
That's what this is all about. Now we're at the front of the telescope. This is it. This is the telescope that did the timing. And this is the point in the video where Steve gets very excited by explaining what up is.
So, okay, the way you use this for timing is you're looking straight up in the sky and the stars are very slowly sweeping across your eyepiece, your field of view. And there are certain stars that are very bright and you use those for timing purposes. You know that this star is going to be at the very center of your eyepiece at a specific time. So when that happens, you mark it and you set your clock
Time.
and you know that's the specific time, right? But how do you get the telescope to point exactly upwards? And it's use something called a zenith tube, right? That's the name for something that points directly upwards. And the way you would do it with this is you would use a mirror made of mercury. So at some point, the light that you focus is bounced off a mirror and then you're looking at the light bounced off the mirror. And because it's made of mercury,
It's flat.
It's perfectly flat.
Well, level,
It's perfectly level, that's right. Yeah, so gravity, local gravity takes care of leveling the mirror because it's made of a liquid metal. And so, you know, the normal line to that plane is always going to be vertically upwards according to local gravity.
And the great thing about local gravity, famously, it can't be corrupted.
No, exactly.
No impact from outside influences, other than the varying density of the Earth. The fact that the Earth's a weird lumpy shape.
Well, it is a weird lumpy shape. But I mean, so you can argue about what's the best definition of up, right? I mean, I would say the best definition of up is parallel lines to local gravity.
No, the best definition of up is goes through the center of the Earth.
Oh, okay, well that's a very modern definition.
Thank you.
Okay,
Yeah,
fine.
but I think it's pretty good. And the issue is, your up, Mercury up,
Mercury up.
does not go through the center of the Earth.
Yeah, so if you take that line from local gravity and you carry it on, you draw it down through the Earth, it will not pass through the very center of the Earth, like
Yeah,
the
you'll
geometric
miss.
center of the Earth, right? Or the center of mass of the Earth, it won't pass through that.
Oh, I would say it's the midpoint of the axis of rotation.
Okay, yeah, well,
It's
we
the
can say
center of
that.
the Earth.
All right, yeah, and it doesn't pass through that
No.
anyway, the local gravity line.
And that causes some problems. That's not even the first zero. Before this telescope, there's one over here. So we've actually got a different line. This used
There
to,
it
I say
is.
used to be zero. This still is zero for the OS maps.
Is it? So Bradley's meridian line. is what
Bradley's
OS
telescope, yeah.
uses.
Because they started in the early 1800s before that telescope had been built.
Right.
And when you're building a new, better telescope, they're like, oh, this one's getting a bit old. You don't want to stop using it while you're putting in the new one. So they don't bother, because this is, the line is...
It didn't matter
It doesn't
then.
matter, it doesn't
Yeah,
matter.
yeah.
And the line is the eyepiece. So they're not going
Yeah.
to faff around trying to get the eyepiece in the same place. They just put in a new telescope over there.
Oh yeah, it'd be a real faff to line it up. wouldn't it? Yeah.
New line. And this isn't the first line. So all the way down there, so that was Bradley's line. This is Halley's line of comet fame.
Right.
Halley's. No, you can see this is getting less and less like a telescope.
This the further back in time you
Yeah,
go,
yeah.
the more rudimentary the telescope.
This is a tube attached to a protractor. Same idea.
Yeah.
And when Halley was using this is the line that lines up with, this is the official reading protractor on this side.
Oh, okay, yeah.
So there's this line. And people were doing stuff that way as well. Every time they get a new, better telescope,
that way.
they just move it down a little bit so they've got space to build it.
Well, in that sense, it's nice that the GPS zero keeps going that
It's
way.
further that way.
This is cool though, look at this, because, so we were
It's a
talking
tube.
about having like a vertical upwards, you know, using a mercury mirror, but another way of doing it, which is much simpler, is to just hang it.
You hang a tube.
So look, it's hung from up there. There's even a plumb line down here, this wire hanging off a mass hanging off this wire. You just line it up with that, and that's how you get vertically upwards.
That's up.
It's not as good as a mercury mirror, but
Well, this one was early
It was fine for this, yeah.
1700s. Yeah, this was like 1720 they started putting this in. And as they got better and better, the line just keeps moving that way. To understand the issue now, we need to understand how you use this line to work out where you are.
right.
Because this line is not a line, as we keep saying. It's just a bunch of observations for exactly what time
A particular
a
star.
particular star goes overhead. And you write that down. We know this star goes overhead at exactly this time. and this star at exactly, et cetera, right? So we have all these incredible timings. What we actually have, the prime meridian, is just a bunch of reference times of stars that move relative to the local noon at the prime meridian.
Yeah.
So if you're over here on your, where's your smudge gone? It's so easy to see. Good work. So what you're doing is working out what fraction of the day difference is the time, local time zones between you and Greenwich.
Yeah.
And that tells you what fraction of the planet around you are. And that's your number of degrees longitude.
Great.
So all you're really doing, and this is why clocks were so important. And there's a whole other story here about Harrison made some clocks. Because you need, as you're traveling around, you can't like phone back. This is pre-radio waves. You've got to know what the time is in Greenwich while you're out and about.
Yes.
Steve then pointed out that I was not completely correct in what I just said, and that solar time zones are not exactly what we want.
You know, so like, okay, you think about, right, the sun needs to turn through a full turn for a day. That's the way we think about it. But in that time, the Earth has moved a little bit around the sun. So to get back, you've got to turn a little bit more. So that you're facing the sun again, right? After a full turn, according to the stars, you need to turn a little bit more because you've gone around the sun a little bit.
I tell you what, should we do it with the globe?
Yeah, okay, great.
Right, so if you start, noon's there pointing at the sun.
Noon's there pointing at the sun, yeah.
You then do a whole rotation like this.
Yeah.
But by the time you get back here, this is orbiting the sun.
Yeah.
So it's actually over here now.
Yeah.
And so it's not pointing
At the sun.
at the sun. It's got to go a little bit further.
Yeah.
And so what we call a day
Yeah.
is slightly longer
Yes.
than a day.
And just, it's going to have to be something like 1/365th of a day. You have to add extra.
To
or
go,
take away
yeah,
or whatever
yeah.
to get the,
And when we're doing things relative to the stars, that's sidereal time.
is that how you pronounce it?
I called it sidereal time.
Because I've only ever seen it written, so that's what I
Yeah,
say.
I said sidereal time, and my wife, as an astronomer, was like, "You mean sidereal time?" And
I suppose she knows, yeah.
I'm like, okay, I'm gonna have to consult an independent
fine,
astronomer. Yeah. So
Yeah.
the reason you look at the stars and you get your timing is you want sidereal time.
Okay.
So actually, if you're out in the middle, now I don't know the practicalities of how they did this.
Yeah.
I'm sure some people will know this in great detail. I feel like we're getting too far off the maths path, though.
Okay, fine.
But you want to get your local time somewhere else
Yeah.
and then compare it to this one.
Okay, great.
And you're right. Solar time is terrible.
Yeah.
We can all agree. So here comes the problem. If the telescope that was used to get the timing of this line was off a bit, I can't help but geometrically thinking about that in terms of it not going through the center of the Earth.
Yeah, so if you're, you've got a line pointing upwards, just continue that line downwards. It's going to ideally go through the center of the Earth, but
not. So I'm going to try and label that. This is what I imagined when you first told me all about this. And this is what I think a lot of people are picturing. And for me, this is what makes the most sense when you say they got up wrong.
yeah.
Okay, there it is. So the plane now defined by, okay, so what I've done, we'll do a spin.
Yeah.
What I've done is if they're here, imagine this overlaps perfectly. If instead of looking straight that way, you're a little bit off, you're going to define this plane, which is no longer a great circle, which is off to the side.
Yes.
Right. And that's what I was picturing when you were saying they're using the wrong up.
Yeah.
But actually, this doesn't matter
Yeah.
because it's all about timing. The only difference was instead of looking directly above, they were looking ever so slightly too far ahead
Yeah.
in the future.
Yeah.
So all their timings were just off by a tiny, tiny amount.
That's right.
So they were actually timing when the stars go overhead of a point about 100 meters that way.
Yeah.
So they didn't actually do anything with this line.
Yeah.
They did another great circle, which is just ever so slightly tilted. Let me get the exact number. Okay, so there's the number of degrees that's out. Divide that by 360. That's the fraction of a day
Okay.
that we're off.
All right.
So we'll just go with 24 hours times 24. It's that many hours off. It's that many minutes off. It's that many seconds off. a third, 0.35 seconds.
So that's how long it takes.
That's how long it takes. Yeah. So for a third of a second, well, we're over there. It's so close. So close. And for all purposes previously, it didn't matter.
No.
Like, it was so incredibly close. So in 1884, we voted in this line, and we all agreed it was good enough, which it was. It was within the accuracy of everything we were doing. Fine. Time advanced. Technology got better. We had satellites. We had radar. We could work out where things are much, much more accurately. Eventually, I think it was like in the 1960s, we started to notice there was a problem. And by then, the tide was turning. So when this line was defined, it was all defined by looking out at the stars. Gradually over time, we did less looking out at the stars and more just looking back at the Earth, measuring the Earth, using satellites around the Earth. And they decided to draw a line at some point, and the name that the official body was called kept changing. But at some point, the powers that be had to just say, stop looking at the stars. And they made that final decision in 1984. 100 years later, they stopped all optical measurements of stars and made it 100% Earth-based. But when they did that, they try and match it up as best they can with the old looking at the stars version. And you think, well, why don't we just put 0 here?
Yeah, you could just shift it all around and decide that's where it's going to be.
Well, you'd have to convince every other location on Earth to change their GPS by 102 meters or whatever it is to solve one issue, and the one issue is tourists complaining. They made the new system fit the old system as best as possible.
Yes, because you've got different lumpy gravitiness everywhere, and you can shift this kind of new definition around to try and make it fit here, but then it's not going to fit there. If here, it's not going to fit there.
You're kind of doing a weighted average of minimizing all the errors. And Greenwich lost 100 meters.
I talk more about this and cover loads of other triangle topics in my new book, Love Triangle, which is out now in the USA. You can see, look, it's very future, Matt, with a copy in Central Park. That's exciting. And thanks to everyone who pre-ordered the UK version, we were a #1 bestseller in the Sunday Times. But what about the New York Times? So if you pre-order the US version of Love Triangle before it comes out on the 20th of August, the fine people who are publishing it at Riverhead, they're running a sweepstakes. If you pre-order it absolutely anywhere, you can enter in to maybe win a Q&A with me online, and definitely I will send you a customized virtual bookmark.
I mean, you got to print your own bookmark and buy your own book. But the point is, I will send you a bookmark. Half of it will be me looking disappointed on the old line, the non-zero line, and the other half of the bookmark will be me on the real line, and I will be holding something with your name on it. I feel like I can write some terrible Python code to automate that. I reckon I can get that down to ones of seconds per name. So unless thousands of you sign up, I'm starting to realize the flaw in the plan here.
You can contribute to the problem by pre-ordering the book absolutely anywhere. I will link to the site below where you can register your pre-order. You will enter the sweepstakes and you will definitely get a bookmark. Participants must be US residents, 18 or older. Other details on the website. And yes, if you did previously pre-order on Mass Gear, I will send you the bookmark as well, just because I appreciate your support.
And that's pretty much it for the video. I mean, we should, you know, the real heroes, we should thank past Matt and Steve. Past Matt and Steve, we just want to say thank you so much for making this video possible. Yes, thank you so much. We're still here on the Prime Meridian, having a great time. Very much enjoyed visiting the Royal Observatory Greenwich, who very kindly let us come in, film on the line, look at the telescopes. Had a great time. Oh, and thanks to Steve. Thanks to past Steve for joining me here in the past at the observatory. And
we're all in the past, aren't we? And people watching this video, it's all in the past.
Yeah, that's true. We're all in the past. Some of us are less in the past than others. Okay. And so thanks to future Matt and future Steve for joining in. And that's it. Thanks for watching.
Great.
And we'll wave. Wave.
All right.
Okay, you check out Steve's channel. What should we watch now? The algorithm thinks you might enjoy this video next.